Yo, what is up, everybody? Welcome to another episode of CCT. Uh, Today we're gonna do another random problem. Today was also the first day of classes in the winter semester at the University of Michigan. It was pretty good. Actually, no, it wasn't. I had a boring 2-hour class. I thought it would be interesting. Professor was not that good. It was a Freud psychology class. It was just a one credit class that I thought I'd take for my one credit of humanities that I need left. I took other humanities. Okay, so without further ado, let's get into this. Let's do some easy problem subtree of another tree. I like to do easy problems on the video, so I've never attempted this, so that's kind of why I like to do an easier problem. If it loads, okay. I've been getting like better at these tree problems, so hopefully you are too by just watching these videos. So, given two non-empty binary trees S and T, check whether tree T has exactly the same structure and node values as the other. Wait, and node values with a subtree. Wait, check whether tree T has exactly the same structure and node values as subtree. Why did they call it a subtree? A subtree of S is a tree that consists of a node in S and all of its descendants. The tree S also could be considered a subtree itself. Okay, let's go to examples because I was confused by that. So given T, return true because T has the same structure and node with a sub. Oh, okay. We're just seeing if. So S is the big graph, and we're seeing if T has a subtree. So sorry. We're seeing, like, you see how this 412 is here, and then the 412 is here. We're seeing if S has the subtree T in it with the same structure. That is interesting. So this is false. Huh. I would think this would be true, but it's false. Even though it has 412, the 2 has something else. Okay, so when it says subtree, it has to be the whole rest of the tree. I guess that is what subtree means. It can't just be in the middle. Okay, so let's see. You could go through and look for if the first value is the same. And then if the first value is the same, you can check if both the left and right side are. I automatically am thinking like recursion. Here, let me make this a helper. Is subtree helper. And I will also take the same thing in. Well, if I'm taking the same thing in, I could probably just pass it. Okay, I might be taking in another input, but if I have the same exact inputs and return value, I should not have a helper. Okay, so my first idea is if the roots equal, so if S val equals T val, then I want to, so now those two are equal. So now I want to see if their left and right subtrees are equal also. Wait. Yeah, maybe. So is subtree helper. Whoops. Let me take this brightness down. S left, T left, and same thing, but on the right side too. Okay. So if they equal and their subtrees equal, So then we could have something like, to make them the same structure, if not S and not T, return true, if not S or not T, because we know one of them, if it gets to this point, then we know one of them is has a child on the left or right, and the other doesn't. So we could return false. Okay, so they're true if they've both gotten to this point, and they're false if they've gotten here. Okay, so this is kind of if they're, so this is to make sure their structures are the same. So if the structure is the same here, that's true. That's if they get to a leaf node together. Then if one of them has a child and the other one doesn't on the same side, then we could return false. And then this is if they both, this is if both of them have values. So if that, but if their values aren't equal, so else return false also. I don't think this is doing it. The reason why I don't think it's doing it is because if it's not equal, it's kind of just stopping. I feel like this is the correct structure, maybe. This is a lot harder than easy. I don't know why this is easy level. This is definitely not easy. I just saw the tree one that was medium. It was way easier than this one. Okay, let's go to the drawing board. So we have 3, 1, no, 4, 5. This isn't even a binary tree. And then we have 4, 1, 2. So what my idea is saying is, like, it's trying to look for the top of it, but if it's not the correct top, it's just returning false. So maybe the better idea is either you are the top of it, or your left or right partner has it. Okay. I think I might have an idea. So, like, if your value, so we're at the roots here. if the values don't equal, you see if this is in either the left or right side. But let's say we get to a point where they do equal here. So if the first value equals, we want to see if, like, this is still S. So S is left and right subtree equals T's left and right subtree. Interesting. Okay, that might be that's an interesting idea. So this is saying if the values are equal, then we see if those two things are the same. Else, not just return false. Okay, this is where we change it. So else return, we're going to do something similar to this, but we are going to keep this subtree intact because we haven't found the head of it. And we're going to look on the left and the right side. I could have sworn I got rid of these. What did I get rid of instead? And then it's going to be or here. Oh, wait. Oh, those are fine. This is where it's different. Okay. So else we're searching in the left side and the right side. This is getting somewhere. And since these are so similar, I don't think I'm going to be changing the return values or anything. Well, let's just make it the real function. Okay, so if, and then we could get rid of these. It's always satisfying when you could like just do quick stuff like this to make things look cleaner and whatnot. Okay, so let's go through the logic again. So if they are both null, that means they both have ended at the same time. You could return true. And if one of them's true, if one of them has a value, this would be this example, like this 0 here. If we got to a 0 on one end, if we got to null on the other end, so that means, so we know both of them can't be null here. So this means if either of them are null, return false, because that can't be the path. So if we get to a part where the values actually equaled each other, so that would be here, let's just see if this would work. So the values do equal each other. So we're returning if the left subtree equals this and the right subtree equals this. So let's just start on the left part. So let me redraw this. 1, 2, so this is S, and then T gets 4, 1, 2. And then what we did was, so then the left subtree, which is just these ones, are going to go in. So then we have 1 and 1, and they're both not null. One of them is not null. Then we check if their values are equal. And the values are equal to each other. So then it goes in here and make sure the left sides are the same and the right. Oh, these are both going the same way. Whoopsie. Right, and then this could be right also. Yeah. And by the way, we do know that they're, we do know that S does have a value. This isn't going to throw an error because we went through here. So anyway, it goes through here. The lefts both equal null. So that's going to return true here. They ended at the same time. And the rights also equal null. And maybe you're asking, how did we know that these values are the same? Isn't this just returning true if the structure is the same? Well, from what I could see, it could only get to that point if the values equaled each other. And I'm gonna think about that with something that doesn't work in a second, and maybe what I just said was wrong, but for now, it's working. Okay, anyway, then it's gonna go, so after it finished the left side of 4, then it's going to go to the right side, and those are both gonna be true also. So we got true and true to pop back to our original stack. Yeah, we got true because the left side was just the ones and the right side was just twos. So I do believe this will work for the first case. Let's give that part a run. Okay, good. Now let's check out what would happen if we had that case. So let me just, actually no, I could redraw this. So we had 3, 3, 4, 1, 2, and now we have a 0, and then that was like 5 here, and then we have 4, 1, 2. So now we will get to the same part where they equal each other, the heads equal each other. So then we want to see if these equals this, which should return true, as we saw in the previous example. But now I want to see if these subtrees will equal each other. So we're in the right subtree. And we get to here, and the values are the same. It's, oh wait, does it? Yeah, it does get there. Okay, so then it's going to go left, left. Okay, so then it's going to go left of the 2, and here it's going to be null, and here it's going to be something. So then it's going to catch here and be false, and that will cause a chain reaction all the way to the top here, so that it's false for this. There's one more thing I want to think about, which is this statement. If the values aren't the same, it's going to return, is the subtree on the left side or the right side? And I think this is also true. Let's try out, and I think this is true because this is just a very recursive thing. So it's like either we found the beginning of the subtree, or by found, I mean this. We're going to investigate it more. Yeah, I'm starting to really like this thing that I came up with. But then if it's not there, maybe it's in the subtree. So let's look in the left and the right. Okay. Does this handle null pointers for both of them? Yes, it does. Return true. What if one of them is null pointers? Handles it. I think this is solid. Let's take a look at what the computer thinks. Computer does not like this one. 1, 1, and 1. I returned false. So I think what this looks like is 1, 1, and 1. So it sees that these are equal. It sees that they're equal. But not necessarily. Okay, it sees that the ones are equal here, and then it goes into here and it's like, oh, one of you had, like the left side, for example, this has a something in it. Whoops, let me get my pen. This has something, but this is null here. So then it's going to return false. So the thing that I didn't check for is if it starts off being correct, but that isn't correct, it could still be there. So I need to do something like, if this is true, you can return true. And then, instead of else, we just look at both sides. So if if you are the start of it, so if this 1 is right here, then return true. Else it's okay. It's okay if it's not. We can continue by looking on either side for it. And I think this is more solid. Let's try it out. Let's take this and put it here. Let's run the code. Oh, you could have a visualizer. That's cool. Nice. Okay. Wait, is there a visualizer? That's really cool. This one? Oh, that's so cool. Okay. So now let's submit this. Let's see if this works. Let's take a look at this. I mean, these test cases are pretty nice to have. I mean, you don't get this in every EECS project, but seeing something like this. Okay, so we have that, and I had this. 3, 1, 2. Interesting. So it's 3, 4, 1, 5, 2. It's like 3, 4, 1, 5, 2, like that. Oh, no. On the other side. Here. And then this one is just 3, 1, 2, like that. 3, 1, 2. Huh. And I returned true, but the answer is obviously false. Okay, let's see. So the first things are equal. Okay, so then it sees if these two are the same. So then it sees if the left and right subtrees are the same. So then it looks here, and it looks here. Oh, God, I think I see this. So then it's looking for... It's basically looking for if this is a subtree of here, and it is. Ugh, dang. But I'm allowing separation between them. Okay. I'm allowing separation between them, which is not what I want to do. I need this to, instead of looking if there exists something, if T exists in S, I need to change it to, does T equal the start of S? So if this is true, and this is true, return true. And if it's not true, then if it's not true, just look at both of these sides. I mean, I didn't want it to come to this, but I feel like I'm looking through every single thing, which is what I didn't want to do. It's basically, this is now looking, if you are the correct tree, like if you're standing on it, that's what this is looking at. And then eventually, if you're not really standing on it, look on the left side and look on the right side. I mean, let's see if this works better now. But I'm not returning anything, which kind of worries me, yeah. Huh. I guess I would just return false at this point. Okay. Let's see how this does. I don't know if taking a long time is good or bad. I don't think it means anything, really. LeetCode is inconsistent with its timing. Okay, so we got another one that doesn't work out now. We're getting there. It's all part of the grind. Okay, 412. No, I returned false on this one. This was the original one. Oh, that's so depressing. But why? It doesn't equal there. So then it goes here. Oh, but neither of these are being returned. Ugh. Okay, I might give up here. Left side. I don't know what to do with this. Okay, well, let's do this. I didn't want it to have to come to this, but I am going to make a helper. Tree node S and tree node T. And that's where I'm going to put this stuff. So if they equal, else just return false. This is going to say if you are literally standing on it. And here I can actually return this. This is if you are literally standing on it. And what I'm going to do is, so I'm going to make this really simple. I'm going to do is Subtree. Oh wait, this is actually exactly what I wanted to do. Return basically is Subtree S. Wait, no. I want to see if you equal it, if the left side equals it, or if the right side equals it. I want to see if any of these are true. So no, this is not taking care of empty subtree, so wait, no, helper is what you need. No, wait. Ugh. Wait, okay, hold up. So if root, here we go. If S, no, is subtree helper S and T. So if we actually found it and we're on it, return true. Else return left or right. Yeah. So, and both of these are going to go through here and check here. So this is kind of pre-order stuff. Does this work if it's empty? So both of these are empty. They're both going to go in here. Yep, yeah, it does. And basically what this is doing is it's going through all the left stuff and then all the right stuff. And if you ever find it, I think it's just going to short circuit. Another way to do it would be if like this, This might be better at short-circuiting it, return true. And then if this, return true. And then just return false. If it's not in any of these, just return false. Okay, let's see if this works. I haven't thought about this too much. Okay. I did not spell return right. That is important. Still did not spell return right. Oh, that's good. It turns blue kind of when you spell it right. Okay, now hopefully we're in business. I have a feeling this just might take too much time. I don't know. Runtime error. No pointer access. No pointer type. So something about no pointer here. Right. So if you have to say if S left is available. Wait, no, you have to say if not S. Wait, if S is already null here, yeah, it should go here because it could technically be null. If not S, then I can return false at this point because T is not it, so obviously it's not going to go anywhere. Okay, let's see if this gives me a runtime error anymore. Can't go. Nice. Okay, great. Doesn't tell me my percentage, which is weird. Maybe it was like too terrible to get a percentage. Okay, so I do want to look at other people's solutions if they found anything cooler, because what mine is doing is it's literally just going through all of the nodes and seeing if any of them, if you're standing on it. Let me, this is, what would be the complexity of this? It would be, well, definitely O of all the nodes in this, so I'd call that O of n times, and then this takes O of, yeah, it would, that's actually not that bad. It would be O of n times O of m, where n is the amount of nodes in S and m is the amount of nodes in T. Okay, so let's look up a C++. Find if same tree. Okay. Wow, okay, yeah, so you basically did that. So if you're the same tree, return true. Wait, but okay, I guess they're assuming that T is never null. Okay, and then they're saying return is subtree left, true, or right. Yep, that's what I basically did. And then to see if they're the same tree, yep, that's what I did. If they're not the same value, return false. Otherwise, do this. Basically the exact same thing that I did. Okay, I don't look at people who didn't put it in code version. Okay. Bool fun. Okay. Is subtree. So if they, you can't do that. Wow, okay, this is just saying if they're both null, return. Oh, this is C. This is not C++, or maybe it is. I didn't know you could return null. So if they're both null, return false? Oh, no, that's true. Wait. No, that's false. Oh, if this is saying if one of them is null, yeah. And then we do check st. Check st sees if they're the same value. Yeah, okay. This is basically the same thing. Okay, yeah, the same thing. Damn, I can't believe it took me that long. My trouble with it before was I kept trying to think of it recursively, but ultimately it wasn't working because the question that I had to ask couldn't be solved in a recursive manner. So saying, like, the question, is this subtree in here? Almost is the same question as asking, if it's not, and you'd know that because these are not, then is it in here or here? That was almost the right question. The part that was bad was that when they equaled each other, so if this was like a 4, for example, when they equaled each other, you had to see if the left subtree was in here and the right subtree was in here, which is not the question you want. You want this to be continuous. You want it to be obviously continuous. So like before I had the error where like a 1 was here and a 2 was here and it was still returning true even though the 4, 1, 2 was really separated. So that is why I couldn't do it recursively. I just had to do it like go through every node and check if you're the same tree at this point, which was annoying. I mean, it is definitely a good problem to do to understand the limitations of recursion. All right, that's all I got for you today. Hopefully you enjoyed my struggling through that problem, and I'll see you next time.